Hello everyone, I'm Zhongqin from the University of Technology, Sydney. Today, I will introduce how we can recognize the three-dimensional orientation of an object just using two RFID tags in multipath scenarios. The passive RFID technique has been widely used for object identification. In this work, we design a battery-free RFID system to achieve orientation sensing, which is very useful for many Internet of Things applications. For example, we can detect upside-down objects in shipment and in storage, especially for some liquid items. Computer vision-based solutions achieve accurate orientation tracking by training a deep learning network. However, this solution is very sensitive to light conditions, especially if the target is partially blocked or in non-line of sight scenarios. Previous RFID-based solutions perform by attaching many RFID tags on an object and deploying multiple radar antennas around a surveillance. However, multipath interference and tag mutual coupling will challenge orientation recognition accuracy. Here, we take an example to show the impact of tag mutual coupling on RFID fingerprint. We fix RFID tag 1 and the move is nearby tag 2 away from tag 1. We can see that the reported RSSI and the phase of tag 1 change with different tag species. In this work, we propose a system that only utilizes two RFID tags and one fixed radar antenna for three-dimensional orientation recognition in multipath scenarios. The 3D orientation includes azimuths and the elevation angles of the two-tag array with respect to a radar antenna. This system could achieve median azimuths and elevation errors of about 29 degrees and 11 degrees respectively. Our basic idea is to leverage the bad tag mutual coupling. If a tag is placed itself in space, its tag radiation pattern is symmetrical along the tag. However, in a two-tag array, each tag's radiation will be changed and not symmetrical. Its tag antenna gain in some directions will be stressed and while weakened in opposite directions. Here, let me introduce how to simulate the radiation pattern of an RFID tag in a two-tag array in MATLAB from an image. At first, we attach a tag on a check border that is used for camera calibration. Then we separate the tag and map the corresponding pixels to the point in a real-world coordinate systems. After that, we can create a tag model on the impedance matching of the tag antenna and the chip. In a two-element tag array, we can excite the tag 1 and terminate the tag 2 to simulate the radiation pattern. Similarly, we can also excite the tag 2 and terminate tag 1 to obtain the radiation pattern of tag 2. The simulated radiation patterns are both substituted back into our RFID fingerprint model to characterize the impact of tag mutual coupling. Next, we propose a deep transfer learning-based solution to deal with multipath interference. Our basic idea is to simulate multipath interference and generate many RFID fingerprints based on the proposed model to pre-train a convolutional neural network. Then we collect a few extra RFID fingerprints to fine-tune this pre-trained network. Once the fine-tuning is over, our system performs orientation prediction with the updated network. To label the training data, we propose a camera-based solution. We bind a radar antenna with a Connect2 camera. The Two-tag array is attached to the back of the chest border, and each tag center is aligned with the corresponding corner point. Our system is built using a commercial RFID radar antenna, and RFID tags. We simulate a large number of RFID fingerprints to pre-train a network and then collect actual samples for fine-tuning in different multipath scenarios. In 3D orientation estimation, one baseline is orientation spectrum, which is achieved using our distance phase model under the tag mutual coupling effect. The other two methods separately use simulated and actually measure the samples to training the corresponding network. We can say that our method fine-tunes the pre-trained network using 133 samples and can achieve lower estimation angle errors than the other three baselines. From the experiment, we also find that the azimuth angle is about 2.5 times higher than the elevation angles error. This is because the tag mutual coupling results in a smaller variation of the radiation pattern in azimuth direction than in the elevation direction. In 2D orientation estimation, our system can achieve about a median angle error of about 16 degrees. In this work, we propose a three-dimensional orientation recognition system using a Two-RFID-Tag array in multipath scenario. We present two key novelties. One is to introduce how to simulate the change of the radiation pattern in a tag array. Another is to propose a transfer learning-based solution to deal with multipath interference. Thanks.